All right, so what is a zero-knowledge proof? A zero-knowledge proof is a protocol between a prover and a verifier in which the prover wants to convince the verifier that a particular statement is true, a statement that's known to both of them, without revealing anything else to the verifier. So that's why it's called a zero-knowledge proof. It's because other than the fact that statement X is true, there's zero knowledge gained by the verifier during the protocol. Now, it's not necessarily going to look like a proof in the classical sense, because a proof, as we understand it, is written, it's finite, you read it and you're done. But this is a protocol, so you might have multiple rounds of interaction between P and V, where P convinces V over multiple rounds that the statement is true. And so in that sense, it might look a little bit more like an argument between the players. And some people will use the word argument versus proof. There's slight technical differences, but both of these refer to protocols. So here's an example. Peggy wants to convince Victor that this transaction X doesn't cause her balance to go below zero. And using a zero-knowledge proof, she can prove this without revealing anything about the transaction, the amount, her current balance in her account, or any of her other private information. And the simplest zero-knowledge proofs look like a sort of challenge-response game. So the verifier gives a series of challenges, and the prover gives a response. And if the prover successfully responds with what the verifier is looking for, after multiple rounds of repeating, then the verifier is convinced that either the person truly did not exceed their current account balance, or they somehow got very, very lucky on all of these different challenges. And if you do enough challenges, then the probability of getting lucky is small enough that you can ignore it, which is what every cryptographer loves.
What they can be used for, specifically for privacy on blockchains. So that is one of the use cases, right? I mean, Eli explained what is the value of having public decentralized ledgers as a means of having a shared consistent view of information across a network of participants. But this need to balance privacy and auditability, and zero-knowledge proofs is exactly the technology that's needed for that. The way that I like to think about it is that you have this decoupling between using the blockchain to enforce a consistency, right? To enforce that everyone has a copy of the same information and can verify that, and that everyone is subject to certain rules for how they can modify or add on to this information. But the enforcement of that consistency and those rules doesn't need to actually involve the underlying data itself. So if a subset of the participants has some of that data, they can prove that that data is being updated according to the rules, right? And that without actually posting that data in the clear to the public ledger. And zero-knowledge proofs are exactly used for that. It's used for because the blockchain doesn't need to perform computation on data. It just needs to verify computation that happens somewhere else.
Could an example be then you've got, say, a state machine where you've got, I don't know, at warehouse, in transit, delivered. And so you've got those three states, and say maybe multiple parties have that, and you can transit from one state to another, and the parties can see what's going on, and you've got this verifiable event on the blockchain, but the observers who are looking at the blockchain can't see anything because they can't understand it. Is that an example, or is that just a little bit too abstract?
So I think that's a basic example where you have a set of parties who want to have a kind of enforced consistency of the information that they have. And that can actually be achieved even just using like Merkle proofs, where Merkle tree proofs, where you don't actually fully need zero knowledge proofs. You need something called authenticated data structures, which allow you to basically verify that you're all looking at the same information, but you're comparing it against some hash value that's actually stored publicly and not the data itself. But where zero knowledge proofs come in to really help is when you want to enforce some kind of rules on how this data can be updated. So you want either a public decentralized network or even just a single server to be able to enforce those rules without actually seeing the underlying data. And so the perfect example of that are how financial transactions have been implemented on blockchains. And so private transactions achieve privacy by proving to the ledger that money is being moved from one party to another, okay, but without revealing who that money is being moved between or how much is being moved. The operators of the blockchain can just verify a zero knowledge proof that this transition of ownership of this money is happening. And that can be used for any transactional system, right? Any transactional system that, for example, maintains records of ownership. So you could have, it doesn't need to be money, it could be any kind of asset, real estate titles, could be ticketing and reservation systems. We have so many examples of I guess business, what in the cloud computing business they call online transaction processing systems, financial networks being one example, where the operators of the transactional system do not actually need to know the contents of transactions if zero knowledge proofs are used. And so actually, I like to point this out that the way that blockchains use zero knowledge proofs to achieve privacy can be valuable for data security in the whole industry of cloud computing. And it doesn't just need to be where businesses want to use blockchains and use zero knowledge proofs in order to achieve privacy on blockchains. It can actually be used to achieve a better form of cloud security, where the cloud can operate a transaction processing system without actually receiving any client data, and it just verifies zero knowledge proofs.